In this video, we're going to talk about how buffer overflows actually work on a computer. Now, I'm sure there's lots of different ways for buffer overflows to actually work inside of a program and on a computer. However, this example that we're going to be looking at here is probably one of the most straightforward and simple ways to at least understand how the process works. Now, I didn't come up with this example right here. This was actually a website that you can freely find online right here, in Interactive Guide to Buffer Overflow Exploitation, which is at this URL right here. Definitely suggest you go ahead and check it out and read through it because the instructions and the descriptions might be a little bit more helpful than what I can provide here. But let's go ahead and start checking it out. So in this example, we are actually getting down onto what's called assembly language. This is the language that the computer actually uses when the processor is performing commands. If you've used scripting or programming languages before, you're familiar with a lot of the ideas about programming. And this basically uses those same ideas, but takes away a lot of the capabilities you have. For instance, in most scripting and programming languages, there is an idea of what's called a variable. Something like that. There's an idea referred to as a variable. And in assembly language, there are no variables. Instead of variables, so no variables. A variable that we might say, for instance, name. So a variable in this case, we would call it name. The idea is basically we create a box, we write name on the side of it, and then whatever we put in the box is, well, whatever we put in the box. At a later date, instead of having to say, hey, what was your name again? We simply look into the box that says name, and it has a person's name on it. In assembly language, instead we use what's called registers. And there's lots of registers that are available on a processor. We're going to be using a couple of them throughout this process. For instance, right here we have an AX, a BX, and a DI. There are special purposes to these, but for our purposes, we can call them essentially generic. What we're going to do here in this first step, or in this first process, is we're going to move data into these registers. So over here on the left-hand side, we have our assembly language. This is the main module, and you can see we're currently at line FA2. If I click step, this command is going to move, MOV, move into the AX register, the number 1337. So if I go ahead and click step, we'll see over here in the AX register, which currently has nothing but zeros, that will have the 1337. Pretty simple. So in the register, we put a value. We're going to do the same thing with the BX register here. So we're going to move into the BX register 7331. So I'll step into that and we see the value over there. And then same thing for the DI register. We're going to move 1995 in there. Fairly simple way of working with the registers. Now, again, some of these registers do have specific purposes. For right now, that's not really too much of a concern to us. We're really just kind of going over the basics of how they work. Sometimes the registers can't hold as much information as we need. Lots of times, the registers can't hold all the information we need, and therefore we come up with this idea called a stack. So along with the registers, and there's only a handful of them in a processor, we can actually have a box of memory in our computer that we call a stack that we put information into. And the way this works is we have about this much memory, at least in this processor, 5,000 hexadecimal, 5,000 bytes of memory. And what happens is we kind of start filling it up from the bottom. So if this is 5,000 right here, we start filling it up from the bottom up. And then, so we're building up a bunch of work in a stack, such as a stack of paper on your desk. What we do is we push onto the stack. So we push more stuff on, and then when we're done, we do what's called popping, and we pop it off of the stack. So let's see how that works. Here in our assembly language, again, we have our main module, and we're going to start off on instruction FA9, and we're going to start by moving this number 1337 into the AX register. So we'll go ahead and start that, and we'll see that that goes into effect. The next thing we want to do is we want to push the value that's currently in the AX register onto the stack. And what will happen when we do that is we see the stack appear. Now, at first glance, that doesn't really mean too much to us, but we had the number here, 1337. Down here in the stack, we still have these values, 1337 in the various bytes. This is a 64-bit processor, therefore there's 8 bytes. The last 4 of them are 1337. Additionally, in this stack here, we can see the memory locations. Now remember, the stack we said went all the way down to 5,000. 4FFF is the very last number right before 5,000. If you're not quite sure about that, it's hexadecimal. You can feel free to research it if you wish. But we see we have 4FF up there, 4FFE, FFD, C, and so on. And then if we were to push another set of information in there, it would actually show up above that. That information will come in handy as we go later. So we push that information onto the stack. The next item we're going to do is we're going to pop the information back off, and we're going to pop it into the DI register. So now when I click step, we'll see the information shows up in the DI register. Now I'm going to walk through that one more time, and this time as we walk through, let's watch the RSP. The RSP is what's called the service pointer, which actually tells the registers, or tells the computer, where the stack ends. Right now it's at 5,000, which is the bottom of the possible stack. Therefore, there's no information on the stack, and the service pointer is essentially saying it's a clear desk, there's nothing here. But watch what happens. So we'll go ahead and we'll move the information first off into the AX register. Okay. And now as we push data onto the off of the AX register into the stack, we'll see that the RSP, or the service pointer, is now updated to a new location. So it went from 5,000 down to 4FF8. So as we put more information onto the service pointer, that will count down. And then as we take information off, it will count up. There we go. All right, so let's continue on, and let's see about doing that with multiple values. So basically now we're taking what we just did, and we're gonna do this with a whole lot more values. In this case, we have 4 general purpose registers. So we have the AX register, the DI register, the BX register, and the SI register, which are operating as just general purpose notepads. And then we have the stack pointer, the service pointer right there. So we're going to start off by moving information into the AX register, and we'll click step, and we'll see information showing up into the AX register. The next 3 commands, if we look through here, is a push, push, push. So we're going to be pushing the values of the AX register into the stack. And now if we watch the service pointer as we do that, so step, we see the service pointer decremented by 8 bytes. We step again, it will again decrement by 8 bytes. Step again, and it decrements one more time by 8 bytes. So we just did 3 pushes. The values were all the same. That's not super exciting, but we did 3 pushes into the stack. And now we do 3 pops off of the stack, and we'll see that the service pointer shrinks as well as the content of the stack. All right. One more special register. So we had some general registers, we had the service pointer register, and now we're going to do one more special register called the IP, or the instruction pointer. And this always points to memory location of the next instruction. We start off, before we actually start, we'll see right here we have already highlighted line FAB. If we look at the instruction pointer, we will see line FAB is the one that is selected. So now when we click step, we should see that FAB will move over to FB0, or the next step, or the next instruction. So step. Not only did we move something into the AX register, but we are also now at the next line for B0. Now this command is a JMP, or a jump command, and it says jump to add 1. We see up here there is a title called add 1, so we are going to jump up to that. And so when I click step, the jump command will take effect. We will be in FA5, and the instruction pointer should be updated as we do that. FA5, one more time, FA9, and then we see another jump for add 2, which takes us down here, and we'll see the instruction pointer updates with those as well. All right. So that's pretty much all of the instructions, or I'm sorry, all of the registers we're looking at. Let's look at one more separate aspect, which is going to be a call. So we had just looked at a jump command. We're going to do a call command, which works exactly like a jump, except it has a way back. All right, so we're going to start off with our move command. We're going to move into the AX register the number 666. All right, so we'll step into that. We see our instruction pointer move appropriately, and then we move on down to FA2. Now in this case, we're going to call sub 1. And we can look down here. Here's our sub 1 category, which will move us down to the command FB3. However, a call command also allows for a return, which should bring the commands back to where it started. So for that return to work, then that means we also have to keep track of where that call came from. And so what's going to happen when we do this call command is not only is our instruction pointer going to move down to FB3, we're also going to put onto the stack what the next step would have been after this call. So let's watch that. We'll watch the stack and the instruction pointer move at the same time. All right, so we just did that. If we look at the details here in the stack, if I look at the actual data, we will see that we have FA7. And when we look at our instructions over here, that is FA7. So that tells the processor, hey, when you see a return command, go back, look in the stack, look at the instruction on the stack, and go to that location. All right. Let's see. So we just added 666. I'm sorry, we pushed 666 into the AX register. We're now going to subtract from the AX register the number 1, or value 1. That's great. And then we're going to return, which will pull a value off of the stack and move us to it. And you see right there, it took us back up to FA7. Well, that's perfect. That's exactly what we wanted, right? Pretty much. Let's do that one more time. We will go ahead and call, and we'll call it this time to add 2. In this case, the stack got updated with the location of FAC, which is this guy right here. So when we reach the next return command, it knows how to get back. And that's how the instructions, or the instruction pointer and the stack, work together in order to keep track of where to go. The next example takes us even further and says, yeah, these calls can be nested, which causes the stack to grow and grow, and then shrink and shrink as things return. So I won't dive into this too much, but we'll watch the stack grow. We'll see the instruction pointers change, and then the stack size change as well. So our first call goes to call 1. We then have a reference back to the instruction pointer, another call, and another call, and another call. And we can see if we went through each one of these memory locations, F98, F98, FA2, FA2, FA8, FA8, and then FAE, which is FAE. So when I do the next return command, first we'll go to that, and then we'll go to that, and then that, and then that. All right, so we do our move, and then we do our first return, and then our second, our third, and our fourth return. And then finally we exit out. Now, one thing I want to mention at this point is we've put two different types of things into the stack. We've put two different types of data into the stack. We have put numbers or just simply data into the stack. Additionally, we've put into the stack instruction locations. Because we're putting both of these in the same place, it can in fact be difficult for the processor to identify which is which. So it is possible that when we're putting numbers or data into the stack, we might be overwriting or replacing information that should be the instruction locations. Well, let's hold on to that as we do one more example here. In this case, we are going to be moving other information into the stack. What we're going to be doing is we're actually going to be prompting or reporting to somebody saying hello. And we're going to be reporting a message that doesn't necessarily fit into a pointer or into a stack or the register. But what we're going to do is we're going to put into the register the location of what we want to store. And in this case, we're actually going to move into the DI register a pointer or an arrow that points to the memory location of a hello world message. We'll see that happen down here in the DI register. Once that's done, we're going to call another function that's not actually shown in this case, but we're going to call another function that will then look in the DI register and print out to the screen whatever is in that register. So we'll see that if we step into it. We just called into the DI register the value 1000 hexadecimal. So somewhere at 1000 hex, we have a message. We're then going to call a separate function here called printf, which will print that out to the screen. That just says hello world. And then we exit out. All right. So now let's start tying it all together. So the first thing I'm going to do is I'm going to call in a function here called say something. Yeah. So we're going to move into the DI register a message saying say something, and we're going to print that out to the screen. All right. I'm going to say hello and hit enter. Very important in this example, at least, to hit enter. What it's next going to do is it's going to say, hey, clear up 8 bytes out of the service pointer for me. Clear up 8 bytes out of the stack so that I can take whatever has just been given to me on the screen and I can store it in the stack. All right, so we clear up 8 bytes into the stack, and if we paid attention, we actually did see the memory location here change. We're then going to move from DI, which is where my hello message was, into the stack. So I'm going to step into moving the information from the DI register into the stack. Excuse me, other way around. Move from the stack location into the DI register, and then we're going to move move 8 bytes into that. We then call the read command, which says, yeah, go ahead and read, and basically says read that location. And we can see from our message right there, I have just loaded up the word hello into the stack. Okay, hey, that works pretty good. Next one, we want to move on to the AX register and the stack pointer. Okay. And then we're going to move again into the DI register by a response. And then call the print command one more time, which then says, you said hello. All right, kind of complicated there, but basically showing how we're able to move information around from the end user. Let's finally tie it 100% together. In this example, we are going to ask somebody for a name, and we're going to call the askName function, which basically does the same thing. It says, hey, what's your name? Prints it out. We then go into the getName function, which is down here, and actually reads that from the screen and returns. We then call the welcome function, which then says, hey, welcome, and then exits out. Now, in this situation, however, we are doing something a little weird and, in fact, incorrect. For instance, right here, when we are saying go ahead and get the name, we are clearing out 10 bytes, 10 hexadecimal bytes of information. We're preparing to receive 10 hexadecimal bytes of information. However, in this step right here, we are accidentally requesting 18 hexadecimal bytes. So we're actually loading in more information than what we cleared out room for. Now, if we remember, that information we're putting into the stack there can be either data or can be instructions. And because we aren't controlling the right sizes of data that we're loading in, it's possible that we may overwrite something or use it incorrectly. Well, let's walk through this and let's see how it works properly the first time. So I'm going to go ahead and step in, and it's going to start off by saying, hey, what's your name? And I'll go ahead and say, yeah, my name is Ed. Hit enter to make sure it works properly in this scenario. It then goes to get name, and it says, yeah, I'm going to request from the service pointer 10 bytes for my stack. It's actually 16, but hexadecimal 16 bytes. And I see right there, so yeah, it's these 2 bytes right here that are getting prepped for me. We then move in the information and read it off the screen, and I can see, yep, right there, there's my name that I went ahead and typed. And then we're going to return the first 10 bytes back in to the screen, or back into the program. We then call the welcome function, which is down at the bottom, which will read those 10 bytes and print it out to the screen. And then finally we exit out. That's the way it's supposed to work. But now this is where the buffer overflows come in. We reset that, and right down here is actually an example of what we will be doing in order to exploit this. So we'll reset this and start it. And it starts off by saying, hey, what's your name? And I'm going to paste in that code right there. Now we have originally 10 hexadecimal bytes, or 16 characters. So that is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16 characters right there, all in A's. I then have some additional hexadecimal information. The /x and then the numbers tells it that it's hexadecimal, and an additional 8 hexadecimal bytes right there. In this case, it is pointing to F75. Let's check this out. Let's see how this goes. Let's see, I'll hit enter, and then we'll continue on. So we call the getName function, and we'll first look at our stack. Right now, our stack has a pointer back from the call function. So it's saying, hey, when this getName function is done, we want to return to F6D right there, because this is what called us, and so we want to go to the next block. All right. Well, as we start reading this in and stepping through it, we prepare for our new information. We then load up our new information, and we will see, yep, there's our 16 A's. But then the next section no longer points to F60 like it did before. It now points to F75. So because we put in more data than what was expected, we overwrote instructions. Yeah, data changing to instructions. It's that simple, once you know how it works anyway. So then we continue our steps, and once we get to the return command, we will see that we actually return back to the exit, and the program ends. It never actually responds back. Now, in this case, that's a fairly benign process, but if I know this program well, maybe I have a test environment where I'm able to test it out myself and be able to try multiple different memory locations. Well, let's go ahead and reset it, and we'll step on through and we'll do something a little more malicious. In this case, I'll go ahead and paste in, and I'm going to change this. Instead of 7.5, I'm going to change it up here to F5.2. Because I know that there's a secret function up there, and I want to see what it does. So we start that. Let's continue stepping through. We'll read that memory in, and as I read it, my memory will change from F6D to F5.2, right like that. I then return it, and I see, oh, now I'm starting up in the secret function, and I step through, and it will actually print out some command that, or some message that means nothing to me, but does in fact show one example of exactly how a Stack Overflow can work. Basically giving more information than it was expecting, and the program not necessarily knowing how to handle it. There is another example as you move further down. Feel free to try that out on your own. That's a much more complicated environment, but it's very helpful.